What do I have to do? Is there a secret? Ah, I did. Well, thank you for coming today. I'm very happy to be here. We now begin our big push after the break. And I've been thinking about the organization of my own thinking. So, a way of thinking is the following: local to global, and sometimes back. In other words, local results give you global results if you're lucky, and global results by restriction will give you local results if you're lucky. And you should know where you are always. I don't, because I'm sometimes chaotic. I don't know where I am. For example, now I have jet lag and I'm in an airplane someplace. Yes. But you need to know where you are. Are you thinking locally or globally? So what does this really mean? In complex analysis, local means that you have a power series development, and maybe it's at a point z0, so you're thinking locally z0, some point, some mysterious domain D, or let's call it U. I'm going to call it U now. And this power series development is local. And this power series development is only locally valid. In fact, we are looking really at the local germ of this power series. We're looking at just, we don't care, any function which has this power series development. It's only local, and in fact, it stops probably at the boundary view because maybe you can't go any further. So it has a boundary, it has a radius of conversion. So I call it local. That's local. And now, how do such local results give you global results? So you know here, this implies we have the local normal form. And this says you change coordinates and that P is equal, after a good change of coordinates, of W to the, well, who knows what the value is here? I don't know. Well, the value, this starts at 0, so its value, P of 0, that's right, plus W to the N. And I'll even write here order of magnitude, order of 0. So P minus P0, it takes on the value P0 with multiplicity O of P. Maybe we write it precisely at C0. So that says that if you have a disk here about C0, some disk, delta, and this is a disk, and delta is a disk in the W coordinates. Then P of this disk is just the translated image of this disk, is certainly an open disk. About P of 0, of Z0. So I should have written here Z0 at Right? I've said way too much about this. It's very inefficient lectures, but I'm really convinced that this is important. Yes, that you have the local normal form, and that means that this mapping P is just a translation plus a mapping of very trivial form into good coordinates. And you see that this thing here, this discussion here, this whole local discussion implies immediately that P that P of U, for this open set U, is open. Because I can do for any point Z1, I have power series development, and I have the same argument. For any point Z2, I have a power series development, I have the same argument. For any point Z3, I have a power series development, I have the same argument. The image of open sets is open. That is a very, very global statement. This is a global statement. Yes. So we have local normal form. I can't say this enough time. Implies global open mapping theorem. Local implies global. And you also know that local normal form implies the maximum principle and this is a form of a global statement. If a function is holomorphic and takes on its maximum, or its absolute value takes on its maximum someplace, it's constant, assuming everything's connected. So quite often we have local results which are really statements about the local ring. I tried to convince you they're almost formal statements, they're algebraic statements about the local ring. Local results imply global results. Now I want to give you a different example. I think new example. I hope I haven't lectured on this so far. Another example. Local implies global. I don't know the history of this as well as I should, but we call this the Schwarz lemma. I talked about it in the notes, and I want to repeat it here as a warm-up. As a warm-up. Have I talked about this in the notes? Maybe, I don't know.
I think so.
Yeah. I think I talked about this in the, I'm sure I talked about this in the notes, but maybe not in the lectures. Whatever it means, the Schwarz lemma. This is not a black lemma. This is a man named Schwarz who was a wonderful mathematician. Well, what is the Schwarz lemma? So I'll formulate it on the disk of radius 1 about 0. I'll formulate it there, but of course there are many generalizations of this. And the situation is this: you have the disk of radius 1. Right? And on this function you have the standard coordinate z. And let's take a function holomorphic on the disk. But what we have learned, I hope we have learned in complex analysis, that you should consider this as a mapping. So it's a mapping, and I assume that it's a mapping somewhere, it's a whole mapping into the complex plane, but I assume it is a self, what we call a holomorphic self-mapping. This is the basis of dynamical systems. You have a self-map of a manifold, and you can repeat it, because it's a self-map. You go to delta, and do it again, and you get happy, and you do it again and again, and it just makes you very happy. You do it n times, and you follow the dynamic of this mapping. So it's what we call a holomorphic self-map. And you assume you scale this thing decently, that f of 0 is 0. You have a fixed point. Maybe you can organize that somehow or another, but let's assume you have a fixed point of the self-map, and you want to understand the dynamics of the self-map, so you repeat it. You start with a point not 0. Well, you start at 0, you understand the dynamics. It stays there. You start with a point not 0, and you start applying this mapping and see what happens. And so you need an estimate. Yeah? And here's the statement of Pfart. It says that f of z in absolute value, here's the estimate, is less than or equal to absolute z. That says that mapping is a contraction in a generalized sense with equality holding at some point, z0, if and only if f is a rotation. So this means f of z is some number, rotation, so I'll write it e to the I phi, so I'm just writing the rotation angle here, so a number of absolute value 1 times z. Isn't that incredible? So you take a holomorphic self-map with a fixed point at 0. Okay? And you want to know what happens to other points. Here's 0, and you start with some point, let's say here, A. And now you look at f, you apply this thing n times at A. And that means f applied to f n times at A, and you find out what happens. And assuming it's, what could happen, this could be a rotation. Yeah, but if it's that, that means that the equality of the absolute value holds at some point, namely at this A, then it holds at every point. It's a general rotation. That's really a special case. And otherwise, you have strict inequality up there. That means you go downhill at each point. That means that it accumulates to 0. That's a beautiful theorem. It's a really beautiful theorem. This is an example of local implies global. Here's the proof. Here's the proof. By the way, this is an example of how mathematics goes. Everybody in this audience here, everybody, I have great respect for all of you. Everybody here could prove, if I tell you this theorem, could prove it. You would come up in finite time. I'm slow, I lock myself in the closet, it takes a week. But you're faster, it only takes you a day. Yes? And then at some point you come up with an idea of G defined to be F divided by Z. Yes? You can do that. That looks terrible. However, you know that F has a power series development at 0. F of 0 is 0. So that means the A0 term in this power series development vanishes. That means you can pull out at least Z. Maybe you can have to pull out Z to some very high power. Yeah? Well, this thing is holomorphic. Now, it could be constant. Right? Well, that would be, constant. That means, I don't know, what is this? Let's just look. Let's look at the supremum over the disk of the absolute value of G and apply a maximum principle. That's a local statement. That comes from the local normal form. Yes, the maximum principle looks at it locally. Yeah, the open mapping theorem says it can't take on a maximum unless it's a constant. So the supremum of this is the limit as you go to the boundary of G of Z. And look, G is F divided by Z. At the boundary, F is less than 1 or equal to 1, and Z is equal to 1 in absolute value. So this thing is less than or equal to 1 at the boundary. That's the proof you're finished. Got it? That's the proof you're finished. It's incredible. What is the proof? The proof is local normal form, open mapping theorem, maximum principle, Schwarz lemma. Okay? Local normal form, everything local to these global results. It's fantastic. Okay? So this is the proof. Okay. Very, very interesting. That's the first thing. It is very interesting. Schwarz found this formulation. In my mind, if you look at the papers of Schwarz, I'm not a good historian, but I've talked to historians who've looked at these things. I think he was the guy who really understood that you should consider a holomorphic function as a mapping. Yeah. Of course, Gauss talked in that way and so on, but and Riemann knew all of it. These people knew, but I think he emphasized it. I think he was the first person to state the open mapping theorem. Yes. But by the way, up to that point, the definition of the notion of a topology was not clear. It was a very, very important thing to have the notion of a topology. What is it? So the notion of openness, what is it? This is probably made precise by Hausdorff at the beginning of the 20th century. In fact, Hausdorff had great fights with Hermann Weyl, Hermann Weyl was a great mathematician, but he didn't pay much attention to topology, and so Hausdorff was constantly pointing out to Weyl that what he was writing there was wrong because he hadn't understood what the right topology was. So they had big fights, very famous altercations between Hausdorff and Hermann Weyl. The fundamental point that book that I would like to emphasize with all of this, where Weyl was doing the analysis, which I will talk about in this lecture. So fights with Hausdorff. I don't know. There's a modern English version, maybe. The idea, the Riemann translation. And I think these were based on his lectures in Göttingen in something like, I write down my father's birth year. But I'm not, this is my father's birth year. Also my mother. So Hermann Weyl gave these lectures, and a Riemann surface, Riemannsche Fläche, is a manifold. Two-dimensional manifolds. You have some examples of this in your taking manifolds. Right. It's a manifold, and Weyl, of course, was talking about Riemann surfaces, and he was not getting the notion of the topology right on a manifold. So Hausdorff was screaming at him, get the notion of topology right. Well, both Hausdorff and Weyl were wonderful mathematicians. So There's a reason for that. That was in the beginning of the 20th century, and the notion of topology and so on was not so clear. And that's one of the reasons that the Schwarz lemma didn't occur so quickly. And now we have an interpretation of the Schwarz lemma. Now, this is probably due to Schwarz, but it's certainly later on due to Poincaré. That's right. These people were talking to each other at this time. Let's take the Euclidean distance that you learned when you were a child. Well, you were Euclid. And from 2 points, d of z w. Now here I'm considering 2 points z and w someplace, I don't know, anywhere in the plane, z and w. Interesting. This distance, if you write it down, is this. Right? If you write it down as this. Let me remind you, if you write this down, you have to recall what that is. This is the square root of this. Right? That's what it is, and that's the usual distance in the plane. So, let me emphasize in the plane. That's the usual Euclidean distance that you learn when you were a child. And the interpretation, I don't know who had this interpretation. I'm guessing Schwarz, Poincaré, Klein, and these people, because later on I can see their thinking in this way, is this the distance from, and now consider, I'm going to write F as phi as a mapping, just to remind you it's a mapping, okay? Yes. The distance from phi of 0 to phi of z is less than or equal to the distance from 0 to z. Isn't that right? Isn't that what is going on? This distance is less than or equal to that. That's the distance from phi of 0. It had a fixed point, so I have a special case here with a fixed point, but it says that phi, so if you're an optimist, you say, my God, phi is distance decreasing. Assuming it's non-constant, of course. Assuming, or a rotation. Right? That's what the statement. Phi is distance decreasing or a rotation. So I'm not here to tell you trivialities like this, but what I am here to tell you is don't beat your head. I see so many, also mathematicians, my colleagues, going, beating their heads against some calculation or against something without looking at what the hell's going on. Right? First of all, local versus global, where are you in life? Second of all, what is going on with this Schwarz lemma? Yeah? Don't just say, well, you prove some stupid estimate. Right? You say, well, okay, you have this estimate, it's incredible, it's a maximum principle and so on, but you can interpret this estimate as long as phi has a fixed point at 0, yes, as phi is distance decreasing, right? Well, okay, so I cheated here. If phi of 0 equals 0, right? Well, that's very optimistic, but you should be optimistic. And so this leads to a very interesting question. And you see, this is the kind of question I would love to see you send me. Question: what should be the distance between 2 points? Is it not the question here? Because the distance, if we have a disk, and we have 0 as the first point, let's call this first point Z1, and the second point is Z2, then in this case, the distance between Z1 and Z2 is we chose to be the Euclidean distance, the distance between 0 and Z2, and we chose that to be the Euclidean distance. And this is just the absolute value of Z2. So the question is, what is the distance from 2 general points? So instead of the situation here, the question, well, I'll leave this here, this is 0 and so on. So the question is here, you have 2 points, both far away, Z1, Z, and here is 0. And here somehow, what is the distance between Z1 and Z2 here? Right? Now that I presented this, isn't this the obvious question? What is the right distance here? Let's say it again. The maximum principle and Schwarz himself realized that you have a fundamental estimate for this dynamical system, and the statement, when we reinterpret it in terms of geometry, and for me, as you know, geometry is mathematics, yes, and vice versa, yes. The statement is that a holomorphic mapping of the disk is distance decreasing, if you're an optimist. But you don't know what distance is. So you ask the question, what is distance? Yeah. And now comes the mentality of Felix Klein. Klein said geometry is symmetry. If I give a course in the intersection between semesters, the name of this course will be Symmetry in Modern Mathematics. And it will be applicable for everybody here as well as people in physics, by the way. Yeah. And so I'm planning to do that. If I think the dean has asked me to do it, and I'd be very happy to do it. I like this course. I like this idea. Symmetry in modern geometry. Well, symmetry in modern geometry was underlined by Klein in something he called his Erlanger program. Achso, auf Deutsch ist nur ein M. Ich weiß es, I never know. Who's here German? One M in German.
No, two, I think.
Two.
Yeah.
You see, there's no problem learning a language when the words are different and the spelling is different. When the words and spelling are essentially the same, it's terrible. So it's called the Klein-Erlanger program.
And I want to underline, there's something to do with the spirit, the vibrations coming through the clouds and so on, some mysterious thing. Because Klein was in Erlangen when he had this Erlanger program. Erlangen is this town near the city of Nuremberg. And it has a great history in mathematics. And one of the most famous geometers, algebraic geometers there, was a man named, I'm underlining the word man, named Max Noether. This is the father of Emmy Noether. Max Noether realized that his child Emmy Noether was a genius. He took her to all conferences, and all the mathematicians around the world got to know Emmy Noether when she was really small. And she was really wonderful. She realized the connection not only of geometry to symmetry, but through that connection she realized the connection between geometry and modern algebra. And modern algebra had not been invented really, and it was invented by Emmy Noether, the appropriate algebra. She's wonderful, and maybe there's some spirit of Erlangen that Klein's Erlanger program is the headline, symmetry, and geometry. Well, it's a very simple thing. If you think symmetry and geometry is the right thing, then you ought to figure out here what's going on with symmetry. If the symmetries are on this disk, whatever it is, we don't see it, then this distance, whatever it is, should be symmetry invariant. It should, you know, distance, and Hilbert realized this, and even Euclid realized this, the symmetry, the distance, the appropriate metrics, and so on, are symmetry invariant. So, for example, if they are symmetries of the plane, they're translation invariant. The distance is translation invariant, right? And if you have the distance on the plane, then take 2 points and take some rotation about any point, the distance is invariant. We have two generators of the group of symmetries. We were just talking about this at Prabhat. This is the same thing as the affine group. It's translations and rotations. Every reasonable symmetry of the plane is a combination of such things, right? And the distance, Hilbert realized this, and he stated this precisely in his notes for teachers, that the group determines the symmetry, the geometry. So the group of affine transformations determines the geometry of the plane and vice versa. So symmetry and geometry is the same thing. That was Klein. That was Hilbert. That was many people, but that's what's going on here. And then you say, what in the devil are the symmetries of this disk? Yeah, what are the symmetries of this disk? We need a symmetry. We don't know the distance, but it should be symmetry invariant. So D should be a symmetry invariant. So what we need to do is this. Let's take 2 points here, Z1 and Z2, that are not 0. Here's 0. And let's map it over here with phi, some other phi, so I better not call it phi. Let's call it, I'll call it T. I'll call it T. I'm going to translate this point Z1 to 0. Okay? Let's translate Z1 to 0 so that T of Z1 equals 0, and T of Z2 is equal to T of Z2. I mean, I don't know where it goes. So here, so let's say here I take Z1 over here by T, and I don't know where, Z1 goes to 0, so Z2 can't go to 0, it goes some other place. Maybe it goes over here by T, I don't know. So that's T of Z2. Yeah.
Do we assume it still goes to the disk? But it might also lie outside the disk.
So,
I mean, T might also map to something outside the disk.
it should not. Thank you for saying this. T should be a symmetry of the basic domain we're considering. So, it's exactly what Nico just said, and it's because of my bad lectures. Of course, I'm implicitly assuming this, but, so, first of all, T should do this. Should translate Z1 to 0 as Z2 someplace. And T, let me write it this way. I'm introducing notation for you for this group. This is the group of holomorphic automorphisms, biholomorphic automorphisms, of the disk. It's just exactly what you say. I require the symmetry to be biholomorphic because I'm doing complex analysis. If I were doing Riemannian geometry or something, I would be required to be differentiable and preserve the Riemannian metric or whatever. I mean, I have no metric here. I have no distance here. I'm trying to find the darn thing. So Felix Klein told me, sitting in Erlangen with his daughter, who's a Wunderkind, told me, not his daughter, that's Max Noether's daughter. So, Felix Klein is sitting in Erlangen, probably talking to this daughter when she's a child. I don't know if they had I'm not sure about the overlap time-wise. I should look that up, whether Emmy Noether had contact with Felix Klein. It's an interesting question. Anyway, this stuff, these transformations that I'm talking about here, should preserve the holomorphic stuff. We're doing complex analysis, so they should be biholomorphic, right? And that means automorphism, biholomorphic. It maps the disk to the disk biholomorphically. So after my chatting with you here. So, after this long discussion, local, global, we have the question is, what is D? And we learned to have a question, what is T? But the real question is there a T? Yes? The real question is there a T? So let me put it here, is there such a T? This is more or less why you were worried about this, because I was using the word translation, and I purposely used this bad word. If you take Z1, okay, Z1 goes to 0, and here's Z2, let's say here's Z2, and now what could happen is here Z2 goes out here. Right, that could happen. Particularly if I really have a translation. Yeah. This is very bad, so T of Z equal to Z minus Z1 would be the good guy. That's the translation that moves Z1 to 0. And it moves T of Z2 equals Z2 minus Z1. And who knows what that is. This could be terrible. You understand, I'm trying to explain to you how to do mathematics, also physics, it doesn't matter. It's the same subject. This is terrible. It moves it out, it does nothing. Yeah? Now I'm going to talk about this problem in great length and explain exactly everything what's going on here in a couple of lectures. And it is the way, finally, that things stabilized at the early part of the 20th century with people like Poincaré. But one thing to do, you have all these lectures in mathematics and all these great professors going blah, 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 and presenting deep theorems, blah, blah, blah. But one thing to do is to guess this thing. Make a guess. Don't, yeah, make a guess. Yeah? So guess what t should be. So guess. Guess what t should be. Yeah? It's obviously not that, because that's going to go out. Somehow what you have to do is you have to take this thing. This is good. You have to take this thing and you have to scale it to make it stay in. And it's pretty clear that if you scale this and you divide, let's divide it. So let's look at z1, z minus d1 divided by some denominator, I don't know, some denominator h of z. So we should try this. And now you're not stupid. You realize that if this thing is high degree, it's not going to be biholomorphic, right? So, I mean, you're going to have zero, you're going to be able to solve equations and so on. So you should try to say this thing is linear. Yeah? It would make sense, because if you have high degree, you somehow it goes away. And it doesn't take you a long time. So here you're in the closet for maybe a week or two. It doesn't take a long time. A week or two is not a long time when Felix Klein didn't really understand what was going on. And certainly our great colleagues of the 19th century didn't understand what was going on here very well. And then you find out that T of Z, a very good example of T of Z, is this thing. Now, my beginning lectures in this subject were in the hands of a great German mathematician, a German Jew who left Germany at the obvious time to Israel and then came to the United States, and I experienced him in the United States, and I like him really very, very much. And this guy, who's, I'll write his name here, Max Schiffer, proved deep results in complex analysis in one variable. It was an applied mathematician also. He wrote this damn thing on the board and told us in the lecture, this is it. This is great. And I looked at this, like, how did you figure that out? Right? Well, I'm going to explain that to you in a couple of lectures. It's very obvious how you figure that out. And Schiffer knew, of course, he just didn't want to bother us with it. But this actually is a wonderful thing that takes Z, that is an automorphism of this. This is something like a generalized transfer. You see, it's a translation, but I had to scale it. Right? Right, and as long as you have the guess that this thing should be linear, then you don't have to lock yourself in the closet very long. You just check what to do. You can probably check that you can scale the first coefficient to 1, and then it takes you no time at all. Okay, so that's the way, one way of doing it. Just guess it. Okay, that's what our professor told us. Max Schiffer told us in those days. Okay, so it's great. We have Z1 and Z2, and Z1 goes to 0, and Z2, I don't know where it goes over here, goes to T of Z2. And here it is, and now we define the distance between Z1 and Z2. By the way, T is almost unique, because if you have two such T's, they both the difference, or the T1 composed of T2 inverse, fixes 0, and it's a rotation. So two such T's differ by rotation. Right? Two such T's, they're almost unique, right? They're almost unique. So almost unique. If you know that, then it helps with your guessing. It's not very hard. So the distance between this, well, it should just be the distance between T of Z1 and T of Z2. This was Klein's philosophy, where distance is defined by the fact that it's symmetry preserving. And this is the distance between 0 and T of Z2. That's what we did, and this we know, that's the distance between, that's the absolute value of T of Z2, and that is Z1 minus Z2 over 1 minus Z1 bar Z2. I just put Z2 in there, right? How in the devil would you ever come up with that? Right? Let's look at the logic. Let's look at the logic. I cannot beat this enough. The distance we know, because of the Schwarz's lemma, the distance between 0 and the point should be just the absolute value. This should be the Euclidean distance. And then we want to figure out between 2 points what should be the distance. And Klein tells us we should look at symmetries that should map the 1 point to 0 and then take the distance. And we make a big theater about this, but there it is, and it's unique. Up to a rotation, but that doesn't change distance. So there it is. And here should be the distance. Let's just write this. Distance between Z1 and Z2. And let's dramatize this. I hope we have something which is very big drama. You see, I was just in the United States, and everything you do there is dramatized. It's just ridiculous. The most trivial things are dramatized. Let's dramatize this, however. How in the devil would you ever come up with this? Well, I just showed you a way. And everybody in this room, for sure, could have done that, right? Well, we're too late. We're about a century too late. But we could have done it, and I claim that we can do it in modern times. We're sitting in front of different problems. It's just we're sitting in front of different problems, right? And so we have to keep in mind, we can make a serious contribution to science if we think in terms of structures, in terms of symmetries, in terms of real thinking and not just calculation. But we have to calculate, of course. The distance between 2 points should be that. Okay. This is a distance function. It is distance decreasing. The holomorphic mappings are distance decreasing. Etc., etc., etc. It's very, very beautiful. Well, this thing has a name. It's so important. I don't know whose name we should really give to this, but maybe we call this the Poincare distance. Now, there's a big question in geometry. I hope you know this question. It's a question probably of Euclid. And it's a question that went unanswered for, roughly speaking, 2,000 years. And the question is the parallel axiom in Euclidean geometry necessary? So does Euclidean geometry without the parallel axiom imply Euclidean geometry with parallel axiom? So there is, this defines a geometry here. We have, this is a geometry, it's a metric. So the question What about the parallel axis? I think it's called the parallel postulate, usually, right? Axiom and postulate are the same words, more or less. I'm not a philosopher, so I don't know. What about that? Well, this parallel axiom says that if you have a line and a point not on the line, you have exactly one line through that point that's parallel. And every child believes that. And now here, you have the disk, and you have a geometry on the disk, and here's the distance, and it looks highly non-trivial. Yeah? It looks highly non-trivial. And you can check if you know, and you can work now. We need to work here. Work here. Now you need to work finally. I lecture here for a half an hour. Finally you need to work, and you ask the question, what are the geodesics in this? What are the lines? Right? What are the lines here? The shortest distance. So what are the lines in this geometry? Okay? Okay. I'm trying to teach you what is mathematics and how to think about mathematics. And so you have some very interesting stuff, and it's my wish that you would ask stupid questions. Yes? And so your stupid first question here is, what is the stupidest line? What is the stupidest line here? Okay. So what is the stupidest line? What is the stupidest line? What is the stupidest line here? Then maybe we can figure out what are all lines. Our model is Euclidean geometry, so if you have any two lines, you can move one to the other by an affine transformation, translation and rotation. So that means we only need to understand one line. Here we only need to understand one line. So at least understand one line. You say to yourself, you're sitting at your desk and you say, I'd like to understand at least one line. I mean, the distance function is not trivial, right? It's really not trivial. I think that's really not trivial. Yeah, but I mean, it's not very hard to see that a line through zero is just that. Because the whole distance thing here, you believe me, because the whole distance thing was defined by zero and so on. So this will be a line. L. Okay, that's a line L. And now we have this terrible thing. We have some automorphism of the disk, phi,
So phi of L, so let's take phi in the automorphism group, holomorphic automorphism group of the disk, which is the isometry group. I'm using these words with respect to the pair. I'm using these words well, not interchangeably. These are two words that you should know. Automorphism this means biholomorphic transformations. This means biholomorphic and preserve this metric. And now phi of L, some phi here, takes L somewhere, right? I don't know. But actually you can check that it looks like, well, we could take a translation and it would take this point to here and this point to here. And so in fact you can really check that it looks something like this. It's obviously nonlinear, right? You see that translation, it's, the generalized translation is some nonlinear thing. And then you have a conjecture here, after you've made some experiments, that phi of L is a piece of a circle. So you check that these things, we're going to check that actually, these translations of this type is a piece of a circle, so it takes lines to circles, piece of a circle perpendicular to the boundary. That's not D here, it's L. Yeah. And now, take this this point here, and now let's apply a little rotation about this point. I mean, we have generalized rotations here, right? And let's move, you see everything's dynamic, let's move this thing around this point. Right? I'm a small movement. So earthquake. Quake. Q-U-A-K-E? I don't know. Is that right? Anybody know quake? You're educated. That's correct, I think. Small earthquake. So we have many such earthquakes. These are many aftershocks. Right? Through here. Right? Many afters. There's a whole family of generalized lines through that point. I just rotated. Here, the family of generalized lines here. Okay. Well, I could do that here too, but that's interesting. Here is a line, and here's a whole family of generalized lines through a point that are parallel to this line. You get it? Here's a line. I drew my picture here. I remember here it is. And here's a line, and here's Euclidean geometry. But actually, here are the lines here that I'm talking about. Oh, it doesn't intersect. They're all going through this one point. Right. Here is a whole family of lines going through this point that are parallel to this line. Parallel means it doesn't intersect. Right. This is a question that Gauss claimed he could answer, but I don't believe it. That in a totally different way of thinking, people from what is now Eastern Europe, Bolyai and Lobachevsky, probably were thinking in a certain way. I'm not sure they did it correctly. But here is a correct model of non-Euclidean geometry. You can check, every axiom is here the same, and the parallel axiom is not valid. I wrote down a line, and then I wrote down a whole family of lines parallel to it through a point.
well, people, Jacobs, it gets on my nerves, are always talking about prizes and Mathematische Olympiade and Nobel Prize and all this stuff. You see, you could get 25 Nobel Prizes for this. Right? It was not only a question of mathematics, it was a question of theology and all of this stuff, whether it was a very deep question. Gauss claimed he had it in der Schublade, that means in the drawer, and he could do it, but he didn't want to do it because it had religious overtones. Well, I wasn't living then, so I don't know. Anyway, this is the so-called Poincaré disk, or the Poincaré hyperbolic geometry. Okay. And it started with local implies global. Yeah. And everybody in this audience could do what I just did here today, if you have the right point of view. Okay. So as I said, I will talk about this, as you notice, I love this theme. I will talk about this in more detail later on. Now, in the remaining time, I'd like to talk about something else. Local implies global. A not so crazy looking crazy definition of a holomorphic function. And the reason it's not so crazy is I'm looking at the viewpoint local to global. Well, we have, for every point in the plane, say, for every point in the plane, we have the local ring. This is very local, and we have power series development here in the local ring. You could talk about this in analysis minus 15. You don't need holomorphic minus 20 or minus 1. You want, here's maybe the set, mysterious set view. Maybe it even has some holes in it. So, this is an example of me because I don't have any hair. But I forgot the wrinkles. Yeah, and you have this power, you have Z0. And you have an open set around Z0 where you have a power series development. Let's call this Zi, Z1. I don't want to start with Z1. And you have an open set U1. And then you have Z2. And you have an open set Z2. And Z3. You have an open set Z3. I'm making a beard here. Z3, U3, and so on, right? And you do this for you cover my face with, oh, that's picturesque, right? You take them off, and I look younger. I've seen so many ads in the United States on television for for making you look younger. And so these are little pieces of plastic you put on your face and you take it off and you look younger. Yeah. So you have PI on UI, power series development on UI, and you have PI restricted to the intersection of UI with UJ. I'm using this notation, which you know, should be equal to UI PJ restricted to UI UJ. So, there's a new definition of holomorphic, not something with linear parts and all of this. It's just a power series development, yes, on a covering, and on the overlap, and for any two of these things, they agree, right? That's the same definition, right? There's no difference. That is the same definition. Right? So that's, in fact, this gives a definition. Of O of U. O of U. Yes. And the idea is you have all the local rings for Z and U, and you go to compatible functions, and you get something in O of U. You went from local to global. Is that not true? I mean, it's completely obvious. You went from local and then some compatibility condition to global. So you have two things. You have Z gets associated to OZ, and you have U gets associated to OSU, and these things are very, very compatible. Right? You have the local ring at every point. You have, it's a little bit better than local at a point. It's more than local. It's just a little bit better. And then you have the compatibility condition. You get O of U. Right? Local to global. So a holomorphic function is such a thing. It's a collection of functions on a representative of the holomorphic function is a collection of such functions on a covering. I'm going to write it down. So a representative of a holomorphic function is a compatible, you know what I mean, but I just talked about it here. And it's a pair. It's a covering and that should be math cal here, UP. Right, a covering by discs, for example, and on each disc, power series or something. And, and so this is, let me just write it here, U is this covering, and P, script P, is these functions. Is a compatible pair. It's a little bit crazy, it's complicated, but it's the way we think, is it not? It's a compatible pair. And then a homomorphic function is an equivalence class of compatible pair. Isn't that the way we've been thinking? Right? Locally, it's a power series development every place. You can't develop the whole thing in a global power series development. You might be lucky, but you usually can, right? And so you say, well, you cover by places where you can develop in a power series development. And then you write it down with the compatibility, and then you have all sorts of coverings. And so you have two coverings and two pairs. Then you take a common refinement where both things are valid, and then you check that it's compatible. That's an equivalence class. That's exactly what a holomorphic function is. Yeah. That's it. The notion here that you're seeing here is, you will hear these words, this thing, this functor is a pre-sheaf which is in fact a sheaf. Now I want to now I'm not going to talk to you about this, but you're going to see this language. Yeah? It's the local global language. It's forget these, I ever told you this. But sometimes somebody's going to tell you that. And what you're going to tell them is, okay, blah, 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 blah. The first example of a pre-sheaf, which is a sheaf, yeah, is this. You have, actually, the local rings can be globalized because of taking convergent power series everywhere, so that I get a function is really a pair, a covering, and a representative of the function is a covering, and on each element of the covering a power series development. And a homomorphic function is then an equivalence class of such pairs. I say that because you think I don't know, for some reason I'm thinking in Italian, I'm matto, sono matto. I am crazy. Maybe some of you, yeah? I thought she was Italian, but Albanian. Well, it's across from Italy. Yes. And you're also Albanian. Did you ever visit Italy? Maybe you just go across. Yeah. It's nice. Do you have a beach where
yeah, we have a lot.
Yeah. What is across from you in Italy? More or less Bari, or how far down is it?
I think Bari is some.
Bari. Yes. This is really the Italians talk about the heel of Italy, of the boot, and make very nasty remarks about Italian. At least my Italian friends. I don't know anybody from Bari, and everybody I know from Italy makes nasty remarks about Bari. I mention this because tomorrow I will recall what is a meromorphic function. And some of you have been thinking about it with your homework, I see, and asking questions. What does meromorphic mean? It's the same thing. You take the local ring. This is an algebraic guy. You take the local ring. It's a unique factorization domain. It means you can. It means everything wonderful. Yes. You can take the quotient field just like we did in analysis minus 25, and you get the rational numbers, but you get here the meromorphic functions. That's the local guy. It's not no longer O of z, it's m of z at each point. Okay? Now, what is a meromorphic function? Well, a representative of a meromorphic function is a cover where you have these things, and on each cover an mi, and they're compatible. Right? That's what I told you. You didn't believe me. That's what it should be. Well, you see with Huckleberry, you think I'm crazy. The reason you think I'm crazy is because given all of this stuff, you have a global representative of a holomorphic function. You can really find a function. But for a meromorphic function, you cannot find that. It's a little bit what you're talking. You understand what I'm driving at? You on each open piece, it's something. It's an mi, and then you have the equivalence class of all this, and you would like to say it's globally a quotient. That's completely ridiculous. It's only lucky here with holomorphic functions that you get it. You understand what I'm saying? It's only lucky that you get it. Every compact complex manifold has no holomorphic functions. Zero. Therefore, it is absolutely impossible to have a meromorphic function as a quotient of two holomorphic functions. The only thing you need to learn, local, global. Global means you piece together local parts. Piecing together local parts is you have a local ring. Yeah. You take the representatives on where they're valid. You demand compatibility. That depends on the cover. Then you take an equivalence relation which factors the cover out of the picture. Right? That's it. That's it in mathematics. Punkt. Yes? That's it. You're extremely lucky in other areas of mathematics to really have a function. You almost never have functions. Right? It's locally, everything is local, good. You're learning manifolds. Locally, you know what it means. Yes. But globally, you may have nothing. So what globally means is you paste together the local things in a correct fashion. This helps you understand with this formalism here, what is a meromorphic function. It's the same definition. Yeah? It's just that meromorphic, you just take the quotient meromorphic, O of z is UF, unique factorization domain, you go to mz, the quotient ring, and then you go to the same construction as above. Covering with valid compatibility and so on. Okay? I guarantee you, you will go in your life and ask colleagues of mine or other students, what is a meromorphic function? And 9 out of 10 will tell you it's a quotient of two holomorphic functions. Okay? That is wrong. It is this. You remind that person that you ask, what if you have a compact manifold? There are no holomorphic functions of a compact manifold except for the compact. Maximum. Okay. So I'm driving this point. I think you've learned it. Thank you very much.